Okay, so we had gotten all of the information gathered on question number 6, and so we're going to just kind of go ahead and graph it. I'm trying to get a little bit better graph on that and get them marked for that. So we begin with the x-intercept. What was the, with the asymptote, that's what we found first. Was there a vertical asymptote?
Yes.
And it was at
X equals 0.
x equals 0, so that'd be the vertical line x equals 0, which is the y-axis. We have a vertical asymptote here. Is there a horizontal asymptote?
Y equals 0.
Y equals 0 is a horizontal asymptote, which is the x-axis. Is there a slant asymptote?
No.
No slant asymptote. Intercepts.
Y or X intercept at negative 2/3 0.
X-intercept is negative 2/3 0. That'd be about right in there. Y-intercept.
None.
Now, that looks like a problem to me because we've got an asymptote at y equals 0 and we've got an x-intercept. So there can't be a point on an asymptote, right?
Right.
So did we make a mistake? I'm going to pause.
Good idea.
Okay, so we made a mistake on horizontal asymptote. I knew better than that. When you look at the parent function portion of this, we would say, well, there's no horizontal asymptote. But we know that a plus 3 causes it to shift up 3. We just didn't apply that. And so my horizontal asymptote is not at y equals 0, it's y equals 3. That plus 3 makes the graph shift up 3. So there's not a horizontal asymptote here. So it's kind of good that we figured that out, that we knew there couldn't be a point on an asymptote. So there we go. So fix that. So we said there was a horizontal asymptote at 0 because if the degree of the denominator is more than the degree of the numerator, then there's a horizontal asymptote. But at y equals 0, but the plus 3 moved that horizontal asymptote from y equals 0 to y equals 3. There we go. We forgot to mention that. Okay, and then we had critical numbers at x equal 0. And we had the interval of negative infinity to 0. And then we had the interval of 0 to positive infinity. And in the interval of 0 to negative infinity, what was happening? It was
Decreasing and concave.
decreasing and concave down. It should have hit that point. And in the interval over here, it's decreasing and concave up, which we can see. We could have plugged in a function value like, let's just say we plug in a 4 right here. We could plug in a 4 and get 3.5, and so we could say, okay, 1, 2, 3, 4, and 1, 2, 3 and a half. There's a point, so we could find a few points in there if we wanted to, right? All right. Any questions on that? Did we find relative maximums and minimums? We didn't find a relative maximum and minimum, and those would be possibly at the zeros of the function. There's only one 0, right? And that was the 0. So it at that point 0, that was at negative 302 and 0. That's not really a relative maximum because it's going up from here, it's going here. So we're going into negative infinity here, as you can see. We're going into positive infinity. If we think about this, there's not really a relative minimum because it's continuing, and right here it's getting below that, so you can't really find a relative maximum in that situation. Any questions on number 6? Okay. Number 7. Now, what I'm going to choose to do on number 7 when we begin to do the derivatives, I'm going to distribute it so we don't have to deal with the quotient rule. But we're going to go ahead and find the asymptotes and intercepts and all that. Okay, so what about asymptotes? The degree of the numerator is
Greater than the numerator.
okay, so for a horizontal asymptote, I'm going to put vertical above it. What would that tell us? If the degree of the numerator is larger than the degree of the denominator, then there's no horizontal asymptote. Now, what about vertical asymptote? That's where there's a division by zero error, or the square root of a negative, so an x equals 0 in the denominator, we create a division by zero error. So there's a vertical asymptote at x equals 0. There's no horizontal asymptote because the degree of the numerator is larger than the degree of the denominator. What about a slant asymptote? If the degree of the numerator is 1 larger than the degree of the denominator, which it is, then there's a slant asymptote. And to find the slant asymptote, you take the numerator divided by the denominator using long division and disregard the remainder. There's a lot of rules here in there. Wow. So we need to study up on our asymptote rules a bit. So we say x is going to x squared x, and then x times x is x squared. We subtract, you get a 0, bring down a 1. Will x go into 1?
No.
No. So we have a remainder of 1 over x, but we disregard that remainder, and so we have y equal x. So we're going to have a slant asymptote at y equal x, disregarding the remainder. Okay? So we have a vertical asymptote at 0, a horizontal asymptote none, slant asymptote y equal x. We want to find the x-intercept. To find the x-intercept, we do what? We let y be 0. So we would put a 0 for y. We would have 0 is equal to x squared plus 1 over x. I'm just going to put that over 1 and create a proportion and cross multiply. So I'm going to have 0 is equal to x squared plus 1. You understand that little piece of mathematics? Get the junk off of x, so I'm going to subtract 1. I'm going to have x squared equal negative 1. Take the square root, and I get x is equal to plus or minus I, which tells me there's no x-intercept. Because those come out imaginary. Y-intercept is the value of y when x is 0. We put a 0 in for x, what do you get?
0.
And division by 0 is undefined, so there's not a y-intercept either. No x-intercept, no y-intercept. Okay. So we've got that recorded. Now we want to find the derivatives. Yeah, I missed the notes. There we go. All right, to do the derivative, we probably would be better to go ahead and distribute that x, and that way we don't have to deal with the quotient rule, so we'll just do that and have an x plus a 1 over x, which is x to the negative 1, right? It'll be a little bit easier to take the derivative of. So the derivative of that is going to be, what's the derivative of x? 1. The derivative of x to the negative 1 is going to be?
X minus x to the negative 2.
So minus x, so it's minus 1x to the negative 2, which is going to look like 1 minus 1 over x squared, right? So I'm going to put it up here so it'll be here. We're going to have y prime is 1 minus 1 over x squared. Second derivative, we're going to take it from the one beside the green there, because we need to do it from exponential form. The derivative of that constant 1 is 0. The derivative of the second portion is going to be 2x to the negative 3, right? And it's positive because the negative times the negative is positive. And so that's going to look like 2 over x cubed. So y double prime is 2 over x cubed. So we got our function, our first derivative, second derivative. We know that there's no intercepts. There's a vertical asymptote at x equals 0. There's not a horizontal asymptote. There's a slant asymptote at y equals x. Everybody good so far? We want to find critical numbers, test points, and intervals. Good? All right. So we'll go after those critical points and all of that. A critical point, you find those in what? First or second derivative? First derivative. Critical numbers. Our numbers that make the first derivative 0 are, and an x equals 0 would make it undefined. A test number, test points, are ones that would make the second derivative undefined, and x equals 0 would make the second derivative undefined. So we can say, well, I have an interval from negative infinity to 0, and then I have x equals 0, and then I have an interval from 0 to positive infinity. And I want to deal with the function, the first derivative, the second derivative, and then I want to make conclusions. And we're going to be looking for positiveness or negativeness within that interval in the first and second derivative. To determine increasing, decreasing with the first derivative, and the concavity with the second derivative. Okay? Are you kind of getting the hang of all this stuff?
Mm-hmm.
Okay. In the first interval, I'm going to choose a -1. In the second interval, I'll choose a +1. If I put a -1 here and square it, or put a -1 here and cube it, then what I'm going to have is a 1 minus a 1/1, which is a 1 minus 1 is 0. If I were to choose a negative, we didn't find all the critical numbers in, did we? We didn't find all the critical numbers. So we got to back up. I knew that. I was thinking that's not the only one. Because of that one, there's another way to get a 0 besides just a division by 0 error. If we let x be -1, we get another 0. So we have another critical number of x equal -1 right there. Well, we found that one accidentally, but we should have found it to start with. So we're going to change our intervals up here. Sorry about that. I was thinking as I was doing that, that 1's going to create a second critical number, and I didn't go with it. That teaches us we really have to be thinking. So we're going to have from -infinity to -1, and then we're going to have x is -1, and then we're going to have from -1 to 0, and then we're going to have x is 0, and then we're going to have from 0 to positive infinity. Now we've got it correct. Left out a critical number there. All right, we're going to choose a -2. If I choose a -2, I'm going to have 1 minus. That -2 squared is going to be a 4, but that's going to make it a 4th. 1 minus a 4th then is going to be a positive number, right? It's going to be greater than 1. So we end up with a positive in the first derivative in that first interval. And I didn't give myself space here. So in the first derivative, in that first interval, then it's going to be positive. If I look at the second derivative, if I put a -2 in here, I'm going to have a negative, so I have a positive 2 divided by a negative something. A positive divided by a negative is a negative, so we will be negative in the second derivative in that first interval. In the second interval, I'm between 0 and -1, so I'm going to choose -0.5. If I choose a negative, okay, so we're going to plug in a -0.5, -0.5. Now, -0.5 squared is positive a 4th, right? So what we have is 1 minus 1 over 1/4. Are you with me there? And that's the same as 1 minus 4, the reciprocal, so you're going to get -3. Okay? So we get a negative right here for the first derivative in that second interval. Now, 0.5 cubed is a half times a half times a half is an 1/8. So you have 2 divided by -1/8. A positive divided by a negative is a negative. It's going to be positive. It's going to be -16, but it's negative. That's all we care about. And so we got negative and negative. In the third interval, we can choose a positive 1. If I choose a positive 1, I get another critical number. We didn't pay much attention to our critical number stuff, did we? We really should have done a better job of getting our critical numbers. So, this is to 1, and then we're going to have an x equal 1, and then we're going to have from, 1 is less than x is less than positive infinity. Now we have all of our critical numbers. We know what we should have done. We know that we should have said 1 minus 1 over x squared equals 0. What would create a 0, the first derivative. And then we should have solved, so we could have subtracted 1, and we would have had negative 1 over x squared equals negative 1. And then we could multiply by x squared, and we would have negative 1 equal negative x squared. And then we could divide by negative 1, and we would have x squared equals 1. And then we solve and get the square roots. We have plus or minus square root. So we have x equals plus or minus 1 as a 0 in the first derivative. So a 0 where the x is would create the undefined situation, but if we set that equal to 0 and solve, we get the 2 zeros, which we should have done. We're not sure why we didn't do that, but we caught ourselves, and anyway, there you have it. We've got those. Okay, well, we'll continue then. We need to be within this interval of 0 to 1. From 0 to 1 would be like a 0.5. If I put in a 0.5, then 0.5 squared is a fourth, and so I'm going to get a fourth, and I'm going to have a 1 minus 4, which is a negative 3. And so it's negative again right here. If I put in a 0.5 here, it's going to be an 8, so I'm going to have 2 divided by an 8, which is really positive 16. But I'm concerned about the positive, so that's going to be a positive. In the last interval, I could choose a 1.5 or 2. If I choose a 2 there and a 2 here, I'm going to have a positive over a positive here, which is a positive. That 2 is going to be a fourth, so we're going to have 1 minus a fourth. That's going to leave me with a positive answer because I've got something bigger than 1 minus something smaller, or a 1 minus something smaller than 1. So it's staying positive. So I'm going to have a positive and a positive. Okay, got all the pieces. We should have found the zeros of the first derivative, not just the undefined. That was kind of weird that we left that out, but we caught ourselves, which was good. All right, now let's interpret what that means in the first derivative. If the first derivative is positive, it means it is increasing. And if the second derivative is negative, it means it is concave down. Okay. In the second interval, it was negative, so it is decreasing. It's negative in the second derivative, so concave down. It went from increasing to decreasing, and it did not change concavity at the x equal negative 1, which means there's a possible it's concave down the whole time. That means there's a relative maximum there at the x equal negative 1, which we will verify in just a moment. Okay? Now, in the next interval, we've got negative in the first derivative, means it is decreasing. It goes to positive, and so it is concave up. If there's not an asymptote there, then there's probably a point of inflection there, right?
Right.
Because it changed concavity, but that could happen around an asymptote, as we know. First derivative is positive, so it is increasing. Second derivative is positive, so it's concave up. There, it stayed concave up. So it's from concave up to concave up. So at x equal 1, possibly there's a minimum point. Okay? We'll find that out in a minute. Okay. Remember that if we take a critical number and we look at the second derivative, we can do the second derivative test. If it's concave up at that critical number, then we know that there's a relative minimum there. If it's concave down at that critical number in the second derivative, then we know that there's a relative max. If it's 0 in the second derivative, the test fails. Remember that. Okay? So we're going to plug in the -1 in the second derivative. That critical number -1. If I plug in a critical number -1, I'm going to have a positive over a negative, which is a negative. That means that it is concave down at that critical number. That means that that critical number is a relative what? Maximum. The idea is that we have a concave down situation, therefore that point is a relative maximum, right? Now that has to do with the second derivative, not the first, but I just needed a place to put it. Okay, now we can do the second derivative test on our second critical number if x equals 0. If I were to put in a 0, in the second derivative, I would get an undefined. So the test fails, therefore there's not a relative max or min. It did change concavity, but it was an undefined situation, which means that there's an asymptote there, which we can look back at our asymptote stuff and say, where was there a vertical asymptote? At x equals 0. So we know that there's a vertical asymptote there. At x equal 1, we can plug our +1 into the first derivative. We would have a positive over a positive, which is a positive. In the second derivative test, it's positive, which means that it is concave up. It means it's concave, it's positive here. That means it's concave up. Therefore, that's a relative minimum. All right. So we got all this stuff. It was a little painful there. We forgot to set our first derivative equal to 0 and get the rest of our critical numbers, but we'll not do that again, I'm sure. Okay. So we're going to leave our conclusions. We'll remember what intervals those were in, maybe. We'll make straight lines today.
I'm trying to figure out if you're doing it on purpose.
No, it's just
That's like it went from 11 cents to 5 to 3.
making it a little challenging, isn't it? A little smart board's having trouble with smart. Want coffee makers. If we were to plug in the -1 to get our exact point on our relative max, we would get -1, -2. And if we plugged in the +1 to get our relative minimum, we would have one positive 2. Okay, so let's start with our asymptotes. We have a vertical asymptote at x equals 0. What about a horizontal asymptote? There's not one. What about a slant asymptote? Y equal x, which is the, goes through the origin, right? Parent function of the line. Bisects quadrants 1 and 3. Thank you. I'm very tired this morning. I've got to go make my brain work. I'm exhausted myself in the shop. No excuse, but I'm not on top of my game this morning. All right. Now we've got our asymptotes. What about our intercepts? There weren't any. So that little green dot in there kind of overlooked. Because I just kind of put it there to find my location to run the line through. That's not really a dot. Okay, and then we have our intervals. Our first interval was from negative infinity to where? Negative 1. And what was happening there? It was increasing and concave down, which means it's going to be looking like that. It's going to be hugging that asymptote and doing something like that, right? Now, where's it going to turn at? That relative max, negative 1, negative 2, right? So to the left of that relative maximum, it is increasing and concave down. And then my next interval would be from negative 1 to 0. In that interval, what's happening? It is decreasing and concave down, and it's going to be hugging that asymptote. My relative minimum was 1, 2. It's right here. That's going to be important to see. That divided the next two intervals. The next interval was from 0 to positive 1. It was decreasing and concave up. That gets us to that relative minimum. Sorry, it got off a little there. Not getting better. And then in the last interval, it was increasing and concave up. So on this side of that, it's increasing and concave up. All right, any questions on that? Pretty cool to be able to graph like that. You can find a lot of stuff. Right, very good. All right, number 8. I may go ahead and move it to the other side. So, number 8, we have y is equal to, it was 8 times
X square roots for 9 minus X squared. Wait, there's
oh,
no
x square roots of
9 minus X squared.
Okay. We can, when we do the derivative, we can do the product rule. We want to rethink this exponentially, so we're going to have y equal x times 9 minus x squared raised to the half, right? Let's talk about all the asymptotes and intercepts and all that stuff first. First of all, Vertical asymptote. What's gonna create an error?
Division by
Division by 0 or square root of a negative. So my values of x have to be my values of x cannot be, they have to be greater than, okay, the values -3, here we go, and +3. The values of x have to lie between -3 and +3, right? Now, that doesn't tell me there's a better vertical asymptote, it just tells me the graph kind of dead ends, right? It's not going to go past there because I will get the square root of the negative, which is an imaginary number. So this really isn't a vertical asymptote, it's a limit to my domain, right? I have a domain limitation because I can't have the square root of the negative. All right. So we need to think about that as we look at the original function. Now, this is not a rational function, so it's not like we have the degree of the numerator, degree of the denominator, and all that stuff, right? We're not really dealing with that because we're not dealing with a rational function. We just have to realize that there's a domain limitation. All right. What about intercepts? What about an x-intercept? Well, it would be when y is equal to 0, right? And that's going to be a little bit challenging to find there, but we can find that. And then we can find the y-intercept, and that would be when x was 0. I think I'll just stop there because we ran out of time, and we will do number 8 next time. That way we can do the whole thing at one time. All right, appreciate your attention. We did well. We made a little mistake, but we found our mistake on number 7. Appreciate your attention.